Let's discuss about alpha particle decay. In a radioactive nucleus, scientists have examined that in case of radioactivity, a radioactive nucleus emits three types of radiation. Two are particles, and these radiations are classified according to their behavior inside an electric field, and of course inside a magnetic field also. I have drawn here the electric field only for simplification. This is alpha particle, and actually scientists have shown that there are three types of radiation. One is positively charged alpha particle. This should be deflected along the negative side of the plate, and beta should be deflected along the positive side of the plate because beta is negatively charged, so negative positive attraction, and alpha particles will be deflected towards the negative plate because it is positively charged. And in case of gamma ray, which is having energy even more than X-ray, and it is very fatal too, this high energy electromagnetic radiation just passes through this electric field as it does not carry any charge. So this is the basics of alpha particle decay. Alpha is nothing but the helium nucleus, beta is the negatively charged electron coming out from the nucleus, and gamma is the electromagnetic radiation, high energy electromagnetic radiation. In order to examine the reason for the alpha particle decay, let's again refer to the stability graph. This is N versus Z graph, number of neutron versus number of protons. We have discussed this in detail in the semi-empirical mass formula video. This is the stability line, straight line, and as Z increases, the actual experimental value, actual experimental manifestation of the behavior of this stability is like this curved line. For lower Z, these two lines merge, but after a certain value of Z, this again becomes like a curve. This curvy nature occurs. And when the nuclei are in these regions, suppose there is a nucleus which is having extra neutron, so it is on this side of this graph, as it is having greater amount of neutron than the protons. So first it will emit neutron, so it will come down by 1, and then again its proton number is increased because neutron is converted to proton. That is the beta decay. Weak interaction is responsible for this interaction. So neutron number is decreased by 1, proton number is increased by 1. So now this nucleus is quite near this stability graph. That means this reaction gives a better stability for this nucleus. Same thing happens for beta positive decay, where a proton decays into a neutron. So a positive charge decreased. It first go like this because positive charge is decreased. Then neutron number is increased because proton is converted to neutron here. So it will move up by 1. So it hits it is almost near the stability graph. So beta minus and beta plus decay is basically to achieve the nearly region of this stability graph, to achieve the stability, more stability. Here we will discuss beta decay in a short while, but now we will discuss alpha decay, where a particular nucleus with Z number of protons and A number of total number of nucleons decays into these two daughter nuclei, This is parent nucleus, these two are daughter nuclei. This is Z minus 2 proton nucleus, and it is A minus 4 as alpha particle carries plus 2 charge and plus 4 nucleon with it. But there is a release of energy also in this reaction. This mass energy of this left hand side nucleus, that is the parent nucleus, is greater than the mass energy of these two products. And this is something in this, in this reaction, greater mass energy becomes smaller mass energy, which is very favorable to nature. Nature would happily decay from a higher energy state, mass energy state, to a lower mass energy state in order to get more stability, because nature always wants to get into more stable situation. And this amount of mass energy is released as energy value for this reaction, which is denoted as Q, which is called Q value of the reaction. But the question is, do all the parent nuclei convert to this alpha particle and energy and other nucleus also in a certain instant? That is, I have this particular radioactive nucleus, and within fraction of second all the nuclei will decay and they will produce alpha particles and energy. Let's find the answer. The answer is, of course, not. All the parent nuclei will not decay into the product nuclei and energy, that is into alpha particle and energy, within a fraction of seconds. It will take time. And we have already derived in our fission video that what is the factor which is governing this decay. And number of decays per second is proportional to n, the number of atoms or nuclei present on that particular instant, which is quite obvious, because if more number of nuclei or atoms are present, then obviously decays will be more in number. And we have already derived this relation. N equal to n0 e to the power minus alpha minus lambda t, where lambda is called the decay constant, which governs the decay of the radioactive nuclei. In the fission video, we already deduced this relation. And we have already deduced this relation in the fission video, the relationship between the half-life and the decay constant. And we have already plotted this fission decay graph also, that how the number of atoms initially present decays with respect to the time in case of radioactive nucleus. Let's come to the alpha particle decay. We have a parent nucleus XZA. Obviously, this is having a very high value of A and Z, and this is undergoing fission reaction. We are getting smaller fragments like Y and alpha particle and some energy. Now this Q is the kinetic energy, and this kinetic energy is distributed among alpha particle and the other product nucleus, which is Y. If we picture this phenomena classically, this is the classical picture. Let us think that this nucleus X is in the form of a ball, and it is emitting alpha and Y nuclei. And this is the kinetic energy, and initially this is at rest. This X nuclei is at rest. So initial momentum of this X nucleus is 0 because it is at rest, and we know momentum P equal to mv, v equal to 0 here. So initially momentum of the X nucleus is 0. So after the reaction, this momentum should also be 0, the momentum distributed between alpha and Y. So alpha and Y must be liberated in opposite direction like this. in order to conserve linear momentum. This is the requirement of the conservation of linear momentum, that these two product nuclei will emit in opposite direction and they will have opposite momentum, opposite value of the momentum. If Py is the momentum of Y and P alpha is the momentum of the alpha particle, that is the helium nucleus, and we call this as P. Now Q is the kinetic energy, which is obviously equal to half mv square, and we know P equal to mv. So P square equal to m square v square. If we substitute v square from this relation, we will get this P alpha square by twice m alpha mass of alpha plus Py square, that is the momentum of Y square, divided by twice mass of the Y nucleus. We have taken Py equal to P alpha equal to P. So P is common, P square is common here. So it is P square by 2 into 1 by mass of alpha plus 1 by mass of Y. And it will look like this after a simple algebra. So P square, that is their momentum value, is equal to 2q m alpha my divided by my plus m alpha. And if we want to find out P, we just need to make a square root of this equation. Now what is the value of the kinetic energy of the alpha particle? We have already taken that Py equal to P alpha equal to P. That is the momentum of the alpha particle is designated as the momentum value P. So kinetic energy of the alpha particle is by definition P square by twice m alpha. This is by the definition of the kinetic energy. And we have just derived the expression of P square, and we put the expression for P square, the value of P square, from here to here, and we got this relation. So this is the amount of kinetic energy for alpha particles. Now let's take a bigger nucleus with X, the X nucleus. It's a bigger nucleus with A equal to 200, and in the N equal to N and Z stability plot, we are at the high end of this stability plot. So we are taking a high value of A, and it is splitting up into two nucleus, comparatively smaller value of A. Y is with A equal to 196, alpha is with A equal to 4. So if we put the values for the masses here, we can find out the energy of the alpha particle, because this is the expression of energy for alpha particle. So for My we need to put 196, My equal to 196 and M alpha equal to 4. So it's 196 divided by 200. So kinetic energy of the alpha particle will come out to be 98% of Q. That means 98% of the kinetic energy of this fission reaction will be taken out by the alpha particle only, and only 2% will be attributed, will be given, or will be achieved by this Y nucleus.